And we are now going to go to the second exercise, where we are going to look at a simple model of gene expression. And so now Rob is joining me.
Hi,
and let's first have a look at the task that is related to what you're supposed to do in the assignment.
Okay.
And maybe Rob, you can open your first template.
Okay, so we've modified the assignment very slightly to be a little clearer. Okay, so let me just prepare my screen. I'll put my MATLAB over the side and I'll put my script file here. Okay, hope everyone can see that. So we have been given this system, which is a modified version of a system that is in the materials, where we have two differential equations that are coupled. So we have the rate of change of x is equal to some parameter g times the variable y minus some parameter b times the variable x. Also, we have the rate of change of y being equal to minus c, some parameter, times by the variable y. We also know that the initial conditions at time 0, y equals y naught and x equals x naught.
Right, and the context of the model, just as a reminder, was that X is a protein of interest that follows the first equation in its temporal evolution, and that Y is a gene expression regulatory protein that somehow influences the expression of the first protein of interest. And we might, as a first assumption, we might think that Y is something that we could use to control the expression of X.
Yeah. So we want to solve this equation to find, instead of our differential equations for both x and y that are just proportional to time and the parameters in the system. So instead of saying dx by dt equals to some value, dy by dt equals to some value, we actually want the value of x as a function of t and y as a function of t. Now, one way of doing this in MATLAB is to use the dsolve function. Now, the dsolve function is slightly different from lots of things we've seen before in that it expects strings of inputs. So instead of typing our MATLAB expression in any other format, we actually need to put it inside quotes. And so we can write it in this way. So dx is equal to g times y minus b times x. So directly translating our equation here into a form that this MATLAB function requires. But we've got two equations, so we need to pass it two strings with two things inside. By string, I mean text. dy equals minus cy. C times y, sorry. MATLAB will think cy is a one element, but actually we mean c times y. We can also tell MATLAB the initial conditions. So x at time 0 is equal to x naught. And y at time 0 is equal to y naught. Finally, we want to tell this function that the independent variable we're interested in here solving over is t for time. Okay? So if we just run that and see what happens, make sure we don't get any errors. Okay. So it's run and it's told us back in our MATLAB window here that R, which is the output to dsolve, has a y and an x component that are something, one by one symbolic maybe. Okay, so let's see what's inside those things. So x and y. Let's run this. I'm sorry. So actually, we can't just call x and y, but these are the way to get these numbers out is r.x and r.y. So from r, we want x, and we do that by r.x. Okay, so if I expand this for a moment, we get quite a complicated equation. Okay, that's gone off the screen even still. Okay, well that's a bit of a pain. But actually we can use another function to simplify our solution, and as you might guess, that's called simplify. And though we're unlikely to be able to simplify y further, let's call it on there. And because I'm going to want these in a second, I'm actually going to name them x and y. Okay. So now let's just run this once more and see what the output looks like. Okay, well, it's a little shorter, the new answer for x than y. It's still quite complicated.
Still quite a complicated thing, and it's very hard to really make sense of this by looking at this MATLAB expression here. So, but what we see is the components that it contains, and I think it's worth to looking at it, because as we remember, this is an explicit solution that allows us to predict things as a function of time. So if we look at it, the time should occur explicitly there, and it does so, but it actually comes in a number of different locations. So we have 1, 2, 3, 4, 5. We have at least 5 locations where time shows up. And as expected, we have a couple of exponential functions, but you can see that it's quite an interwoven thing, and it's very hard to make sense of by just looking at it. So fortunately, by having it in MATLAB, it's available for us to be used and to be investigated further. The y expression, on the other hand, can you just highlight it? The y expression, on the other hand, is just of the form that we are used to, the one that we know, right? Because we have seen that this is the solution for a first-order linear differential equation, and it has the decay rate minus c, and the half-life, you would be easily to tell that this is something like logarithm of 2 divided by c. Okay, let's continue.
Okay, so I'm just going to clear the screen for a second to make everything easier to see. I'm just going to output this again so we know what's going on in there. Okay. So the next part of the problem says to consider the system when c equals 0.1, b equals 1, g equals 1, x0 equals 0.1, y0 equals 10.
So we are now thinking of actually simulating the thing and actually making some graphs.
So there's a number of ways of putting these numbers into the system. We're going to do the one that we did last week.
Yeah, we did.
So we first of all need to tell MATLAB that although it seems to have worked out that some of these elements are symbolic here, we actually want to be able to work with them now. So we're going to have to just define them as symbolic elements again. So using the sims command, we want C, B, G, and this, I'm putting this on a new line just for no particular reason, X naught, Y naught, and T. So they're all of our symbolic elements in our equation so far, the parameters in the equations and the implicit T. Now we're going to use our handy MATLAB function to convert the expressions here into functions that we can then use numbers with. So I'm going to call this my, use our MATLAB function to convert our symbolic expression into a MATLAB function. I'm going to start with y. I'll come back to x in a second. We need to tell it that we're going to be using the vars. I forget what that means.
Variables.
Okay. And then we need to pass it the variables we're interested in. So y0, t, y0, and c. are the only variables that come into this y expression, y0, c, and t. Okay. But of course, we can't plot this function as it is because it has 3 variables. And we know from before that our fplot function, to plot a function, requires functions with only one variable unknown. So we're going to assign numbers to our variable. I'm going to call this fy by using an anonymous function. So we want a function where the only thing that is unknown is t, and I'm going to pass it the previous function my with t unknown, and then y0 is 10 and c is 0.1. Okay, so that function is the function that we can use in fplot. But first of all, I think we should do the same thing for the x variable. So mx equals MATLAB function. Now we're going to pass it x. Again, use the argument vars. And now we know we want t, but we need to figure out which other things are in our expression. So we've got t, b, c, x0, c, c, g, y0. So I think that's all of them, isn't it?
Yeah. So the interesting thing is now that we need to know both the initial concentration of X and of Y. We need both of them, right? Because the X concentration depends on both Y and X, so also the initial concentrations need to be given. And of course, all the parameters that are in the equation, they show up as G and B, but from the second equation that controls how fast Y is consumed, we also need to know the C. So everything needs to be now handed over and specified. G missing, yeah.
Yep. Again, our fplot function only wants one variable unknown, so I'm going to make a new fx function at t. So again, an anonymous function with only t not set. Call mx with t unknown, x0 0.1, y0 10, c is 0.1, b is 1, and g is 1.
So here it's important to be careful. The order of the numbers is of course given by the way the arguments are passed. So t comes before x0, comes before y0, and so on. And it must be the same number of numbers as the specified number of arguments. So if t is left to be non-specific, then we are left with 5 numbers, and it must be the same number. If you do that wrong, of course, there will be an error, and it's a frequent error actually, so best to check directly
I think
correspondence.
it would help just a second to go back and explain what we've done so far. So given an initial system, we've symbolically solved that using the dsolve command with an implicit variable t. Simplifying the solutions has given us these equations here, these symbolic expressions. Next, we've explained to MATLAB what our symbolic parameters are, and we've used these to set new MATLAB functions as opposed to symbolic functions based on the original symbolic functions that were the solutions to our original equations. Then, in order to use the fplot command, we need a function that only has one unknown variable, t in our case. So we've made new anonymous functions where only t is unknown and the other parameters are set given by our original question. So now all is left to do is to actually plot our solutions. So we're going to use fplot, and fplot requires limits. So I'm just going to set them here, limits. let's say between 0 and 50, shall we? I want to plot both on the same figure, so I'm going to do hold on, and then f plot. So I'm going to get f of y, the limits. I'm just going to put this up the screen a bit more. Also, I haven't spelled f plot right. And let's give it a color. Let's say black. K for black.
Okay, let's think for a moment, what would we expect this to be? So actually here, because this equation is easy, we can actually even predict it without seeing the plot. Let's look at the highlighted function, but what we are going to see is an evolution of the concentration of y starting from the value y naught. You have specified the value of y naught, and if we just look back at it, it's specified as 10. So we must expect, it's specified as 10. So what we have to expect is that for time being equal to 0, so when the starting point of the simulation or the function, and this actually shows the output, the starting point should be at 10. Y should be equal to 10. And we know it's a temporal evolution, of course, if we know what an exponential function looks like that starts at 10 and then decays with minus c times t. So I think it's unlikely that this function is ever going to grow because of this minus in the solution. And if we know how this function works, we will also not be surprised if it decays to 0, because that's the end of this function mathematically. So it cannot go negative if we start from a positive initial value. So maybe you can just execute the script so far and see whether what we get is also what we expect.
That looks about right to me. So we start at 10.
Starting at 10 is the initial condition, and we have a temporal evolution that is decaying. It's not decaying linearly, it's not in a straight line, but it's, of course, following an exponential decay because you have the exponential function here. In the long term, we'll have it reaching 0, and we can already sense that this will be happening. So we might simulate much longer, but of course, following an exponential function, it's no surprise. It will reach 0 for very long times. Actually, it reaches 0 at infinity, but as we are in a real world, in a noisy real world, it would reach that level much earlier. How about half-life? What can we say about its half-life? We could actually calculate the half-life. Shall we do it?
Yes, so it's log 2 over c naught, and c in our case is...
Over c.
Over c, sorry. C in our case is 0.1.
And we had specified c as 0.1 for this calculation. So this gives us a value of 6.9. What does this mean?
So this means that we have the half-life, so the time it takes to drop by half, so say 10 to 5, if you follow that across, about here, follow it down, it'll be about 7.
After about 7 time units, approximately, it's just roughly, but after about 7 time units, this graph should reach the point of where the concentration is actually equal to 5. So yeah, thank you. If you just use the line tool in MATLAB, you just draw a line, and then we can see that, that will be approximately right. And visually, we are somewhere between 5 and 10. And we can see that the exact value for this function is 6.93 and so on. So we understand, of course, that C directly impacts on how fast this thing decays. If C would be much larger, of course, it would take much longer. It would take much shorter to get to this point. We'll be there much faster. And if C is much slower, then we'll take longer to get to this 50% mark.
Okay.
Okay.
Once we just finish our script off by plotting x as well. Let's say red. Okay.
Use another color.
Okay.
Now what does this show us? Okay, We can see both graphs now.
So the black line is our the line we had before, which is the equation for the solution for y, and now the red line is the solution for x. So that increases initially and then decreases.
Right, so why is this happening? Why would that first increase and then decrease?
Well, it's directly proportional to the amount of y in the system. So when y is large, we have an increase, and then as y gets smaller, there's not enough y to make a positive impact on the amount of the production of x in the system, so that decreases.
Exactly. Y was this regulatory molecule that turns on the expression of this protein called X. So we'll get a lot of it as long as Y is there in abundance. But once Y gets lower and lower, gets consumed successively, then there will be a time point when the expression of X reaches a maximum, means it will no longer be supported to grow. So its concentration will start to decay. And because the regulatory molecule Y is going to zero, eventually also the concentration of X will follow and also go to zero, if the model is correct, namely that all of its production depends on the presence of Y. So we have a couple of features. We have this Y exponentially decaying and the X variable actually first rising, going through a maximum, and then decaying, and also similarly in the end showing exponential decay, which is a feature that we now can use to quantitatively predict how the relationship between these two will work. And you can already see from such things, similar things might of course happen in very different contexts. We mentioned the action potential in neurons that doesn't follow a linear growth, but an exponential growth is actually an explosion here. And we could also think of the concentration of pharmacologically active substances in the body that are described by various similar types of models and that follow similar paths. And you remember the half-life is one thing that, of course, has then to do also with the peak, where this peak happens, namely because X depends on Y, then the half-life of Y will directly impact where the peak of X is and how high the peak is. So I think we've done quite nicely in looking at the system by use of its analytic solution. So we have investigated properties of a specific model, even if it was a very simple one, but assuming that MATLAB is able to actually give us the solution, so we needn't worry so much about the numerical simulation.